Hi, welcome to the Calculus 3 lecture series. And we are in the unit Vector Calculus. This is the second part of our lecture number 4. We talk about the line integrals. And for the first video, we talk about the line integrals over the scalar field. And now for this video, we're going to talk about the line integrals over the vector field. Okay, so now let's go to our lecture notes and let's get in start. All right. Okay, so here, let's start here. So let's do a quick capture or review what we learned from the video number 1 here. So this lecture we talk about is the line integrals, right? So in here, the line integrals, so we're going to talk about the line integrals over the two things. Here is the line integrals under, we call this the scalar field. That means it's just in our typical R2, R3, and you have functions here, right? So we said, the way the key things here to do that, so we use this notation, right? So we say if you give me a curve C, then I'm going to, for example, this is the R2s, right? So XY to the DS is here. Okay, so like we say here, be careful, right? This is you use the arc length to do that. Okay, so now we say in here, then we said the problems here. So under the scalar field, we say the hardest part is try to find the parametric form of these curves here. After you find it, then this one we can say this is just you switch everything to what? To the t's, right? So we said you replace the xy with a function of xt and yt. And because this is doing the arc length here, we say here you will do, this is just the dx dt square plus dy dt squares here, right? So that's what then in here, be careful what we are integrating against right now, how we change it to a dt's here. So after you transform that, then this will just be a very, very typical calculus 2 integrations, right? You integrate, you only have one variable, and then you integrate over intervals here. Okay. And also we talk about, there are two other, the line integral under the scalar field. And so you can do is like an integration under the x-axis or integration on the y directions here, all right? Okay, so now let's take a look at the next topics. That's the current topics we're going to talk about under this video. So we're going to do the line integral under, we call this the vector field. Okay, so from the, I think the two videos ahead, we talk about what is vector fields, right? So vector fields basically is you have a, this is like an F, that's the vector form. So for every point x, y here, you have a defined functions. This is what we call, is the real scalar function, like the components functions, right? So then this is the I components plus Q, X, Y, and the J components, right? So we say, the domains here is all the, in the domain of the R2, so every points, right? So this one, so we say this is the point here. So then every point you can have like you create vectors here. Then you can graph the vector. We also said, if you use the, the vector software, you use the graphing software, it's a lot easier to see those vectors, feel what it looks like. Okay, So now, if I have integration over the vector fields here, right? So now let's take a look. How do we do that? Okay, when we do the vector field, so this is how do we write the notations here? So we have a C's here, all right? So let's say it's the curve. You're going to do the vector, you're going to do the integration. Now, instead of the function, so you have like a f like here, the vector field function, right? So this is a vector field function, x, y here. So you have like the I components vectors here, right? So this one's here. So then you dot product your r dr. So what is the r against here? So this r is the same like when we doing the integration over scalar fields, right? So the RT, so what is this one's here? This is a parametric form. So this is the parametric form of what? Of your curve C here, right? So this is a parametric form. So it's a vector also, right? So like this one's here is a vector also. So that's why we say, okay, this is how do we define the vector field. Okay, so it's this vector field dot product, the derivative of this parametric form. So the way you can write it is like this way. So that means still, because this is a parametric form, T has a starting point and T also have a stopping point, right? Okay, so this one you can rewrite like this is the AB, right? So then what you do here, okay, so you replace the F of here, you put the RT inside. Okay, so just like we did here, very similar, right? It's just because in here, look here, right? So in here, we said, hey, you replace the function of x with t, you replace the function y of the t. So here is the same. You replace your pxy with the whatever you defined in the RTs, right? And then in here, you dot product, right? R. So this is a vector also, right? So you R prime T's here. We know when you dot product two vectors, what you're going to have, you're going to have a constant because you add them together, right? Now in here, take a look here. Now this is how do you change to everything to the t's here, right? So it's the same strategy like when we do the scalar field. So now in here, you can say this is r prime t's here. There are a couple different ways you can do it. And so there are several methods here. The method number one is here. You can do these ones, right? So this is, let's say, this is our definition method. So this is method number one. So you can have it in a different way. They will give you the same things here. Okay, so what is this one's here? So this one's here. So if we say the T, this one's here, T is a unit. So if we say T is the unit tangent lines here, okay? Okay, so if the T is the unit tangent lines, okay, so it's the unit tangent vector, right? So it's a unit tangent vector, okay, to the unit tangent vector function for the C's here. Okay, so now, so this ones here, you can change that to the C F of dr. Okay, so you can do like this, I guess. So let's say instead of writing all that, we said that this is F dot dr, right? Dot dr. You can write it as this way here is like AB. Okay, so this is the F dot T here. But in here is like I'm using what? I'm using the arc length here. So it's the same way like we did before. If you want to use you can use the arc length. So what is this one means here, right? So here, let's take a look here. Let's do a quick graph to show you. Okay, so this is X, Y, and Z's, right? And now this is my curves here. Let's do here. Okay, so this is a curve here. This is my C curve. So start from P0 to the PNs here. Okay, so now in here you have like, just like we did before, you get an arc, right? So this is I, point I minus 1 to I here. So you try to predict, you try to use this arc, right? So this is the arc. Okay, so instead of using the arc, then you you find the tangent. Okay, so this is the tangents here. So this is the tangent at TI stars here. So you try to use this tangent. The reason why we put a unit tangent line, because I don't want the magnitude of this affecting that. So that's why in here, this is the arc. So that's why we say this is the ds here, okay? Okay, so this is the other way. We're going to take a look at the example and show you how do we do each one. So let's be careful. This is kind of use the arc length again, right? So that's why we put the ds, okay? And then the next ones here is the method number 3 here. So we can do this also. In fact, sometimes this method maybe is the easiest one if you cannot find the, the parametric form. So this one's here, right? So we said if I want to do the f dot, okay, so f is a vector, the dr, all right? So these ones here, you can just do, if they do give you, if they do give you this, like the functions, like the vector functions here, if they do give you that vector function, then what you can do is here, will be, you can integrate, you're just integrating the line integration to the components functions, right? So you can do, this is the P, and this is dx plus q, this is dy. So we know how to do this P. So what is this one going to change to? It drop to what? It drop to, the scalar field, right? Because here, this is just like the P, it's a real value functions here, all right? Okay, so now this, let's take a look at what we just did. And then let's go to the next sections here, next slide, and let's kind of review what we just did, okay? Okay, so now let's go to, here is the summary about what we just went through. Okay, so let's see anything different. Okay, so we said this is the, so here, take a look, this is our what? So this is our definitions about the line integral over the, the vector field. And so we said you can just replace the RT and R prime T. That's what we just did. Then we said there are two other ways. So otherwise here you do the F dot T, and then be careful, this is ds. Or you can just use the components functions here. And the last things here we talk about is also the physics applications here. So, if the F is like a force field, okay, so we know the, the force times distance, in the basic introduction of the physics, we know force times distance is work. So here is the same. So F dot dr is the work done by the force F moving the particle along the curve C. All right. So that's just one of the physics applications here. Okay, now let's take a look at some practice problem, some example to see we'll be able mechanical to do that. Okay, so now I want to evaluate the line integrals, okay, from this vector field. So this is the vector field, and the C is a curve defined by here. So I did graph it for you. So if you, the blue, blue vectors here, right? So the blue vectors here, those are defined by this vector field. Then the red curves here, this is my C's, right? So that means I'm going to integrate along these red curves here. Okay, so let's take a look at the mechanically, we know how to do it, right? So we know the FRTs here. First things here, I need to replace the FRTs here, right? So FRT, F here, this is X and Y, all right? So what is my X here? X is T, and what is my Y? Y is T squares here, okay? So this one's here, so what are going to be? X times Y, so it's T times what? T square, and this is be my I components. Then plus EX square, right? So this is a 4, and the E, what is X squares here? E to the T square. So this is my what? This is my J's here. So my f of x, y, I can change to this is T3 I components plus 4E T square J components here, right? Now, the next thing here is I'm going to take the derivative of this vector function RTs here. So we know from the first couple videos for this unit, we know the derivative will just be, you take the derivative for each component. So this is 1, when you take the derivative, this is my I components plus 2t, what is here? This is my J components here, right? Okay, so now, we said the line integrations over the vector field will be FRT dot product R prime T's, right? Both of them are vectors. So let's put it this way. Maybe it's easier to see the dot product. So this is 4ET to the square. You dot product what? 1 and what? 1 and 2 t's, right? Okay, so you just times each one. So like I said, become constant. So T3 plus 2 and 4 cancel. You're going to have 2TE T2. Okay, so now, because they have defined the T for you, so that's nice. So I change the whole things here. So I said I'm changing the line integration from F dot dr, right? Okay, so from F dot dr, what I changed to a single variable basic integration like we learned before, right? Okay, so from the 0 to where? 0 to 2 here, right? Then what do you have here is T3 plus 2 TE, the T2 here, dt. So both of this is pretty simple to integrate, right? So for this integrations here, basically you just use the what? We use the U sub, right? So you sub the U is equal to the T square, and then you can do that integration, and you will get this, it's pretty easy. So I did that, and so the answer, I'm not going to spend the time in here to show you how to do the U sub. So this will be e to the 4th plus 15th here, okay? So that is what we talk about is the line integrations over the vector fields here. Okay, so now let's take a look at the next ones here. So next ones here, I have a line segments, right, from 0, 0, 0, 1, 7, 2. So, and this is my vector field here. So I'm not going to evaluate the vector field integration over these lines here, this line segment. So I'm going to do the 3 definitions, and amazingly, they'll give us the same answers here. Okay, so like for here, we know the hardest one is to try to find this RTs, right? So this is the hardest ones here. But, you know, this one is not bad because we know very well how to find the lines here. So what is the direction vectors here? So 1, 3, 2, right? So it's 1 minus 0, 3 minus 0, 2 minus 0. Then you can choose a point. I choose 0, 0. So my line, so the RTs here will be what? Will be 1, right? So the X is here, so IT is here. I can do like this. Okay. Okay, so the X here is 1T, right? So it's 1T. This is my I, right? Then J is Y. Y is what? It's 3T, right? So this is my J, and the plus, you know, what is Z here? This is 2T for my case here, right? Because I know the lines here, right? So I know the line, the parametric form. So we know the parametric form of the line is equal to x equal to 0 plus 1t, y is equal to 0 plus 3t, and the z is equal to 0 plus 2t, right? So that's what you substitute over here. And because we mentioned in the previous, because this is line segments here, right? So because this is line segments, that means it's not like a continue going line. So what is my domain of the t is from 0 to 1. Okay, so now let's try to use the first definition. The first definition is going to be FRT, right, dot R prime t. See here. Okay, so let's see here, FRT. Okay, FRT, I'm going to, so, okay, let me color code that. This is X, this is Y, and this is Z here, all right? So the FRT, first one is Y plus Z, Y plus Z, so what is here is 5T, right? Then the second one is 2Z, okay, 2Z plus 2Z plus, I think this is, there's a misprint here. So this is should be 2x plus z here. It's not 2z plus z. So it will be 2x, so it's 2t plus 2t, so it's 4t. All right, okay. And then the last one is x plus 3y. Okay, so x plus 3y, x is t, 3y is 9t. So what here, I have 10t's here. Okay, and then dot product r prime. So what is the r prime? You take the derivative. This is 1, 3, and 2. Correct? Okay, so now your dot product here will be 5t plus 12t plus 20t's here. So total how many? 37t's here, right? Then my integrations will be pretty simple. So this is the f dot dr, right? So this dr. Okay, so this is will be, you change everything back to the t. Wow, we change this to a super easy integration. So just 37t dt. So when you do that, you will get this is 37 over 2 here. Okay, so now let's take a look at the part B here. So if I can find the unit tangents, right? So I know r prime t, right? So r prime t, just like we did before, so it's 1, 3, 2, okay? So I need to find a unit, you know, the t is a unit, so I need to find the length or the magnitude of the r prime t. So the magnitude of here is what? It will be 1 plus 3 square plus 2 square is the square roots of what? square root of the 14. Okay, so now I can say, okay, now this is the tangent, this is the tangent vectors. So because I want to find its unit, so it's every1 divided by square root of the 14th, right? So this is my unit here, unit tangents here. This is 2 square root of the 14. Okay, so now because remember during the review, we know the TN, if you use the, if you use like the TX here, what you have here, so you use the, okay, so you use the TX here, you will have like a, well, okay, so this is like, okay, let's come back a while ago. I guess got an internet interruption and kind of stopped the screen, and I almost thought I lost all the recording. That would be pretty bad. Okay, but anyway, so that's good. I hope it recovering well. Okay, so like remember a while ago when we defined if you do the arc lengths, right? So when you do the integration, you need to do what? You need to find what we call this ds here. So the ds here will just be what? Just like we did before. So it's dx dt square plus dy dt square and plus dz dt squares here. So if you find this one, so this will be what? Square root of the 14 dt. Okay, so now we can do that. Okay, so this is basically the same like the first one, right? So the FRT, right? So FRT still is the same. What you will have here, you will have a 5t I plus 4tj plus 10tk, right? So this is my components here. And then now you do f dot t here. So f dot t will just be the 5t, 4t, 10t dot. What is my t's here? Here, great. Right, so this is 1 over 14, 3 over 14, and 2 over 14 square root of the 14 here. So you will get this one here is equal to what? It's 37t over the square root of the 14. Okay, so now I'm finally integrating f dot dt here, right? F dot t, right? So we said this is f dot t, then is what? Is respect to the ds here, okay? So now let's do the same things here. So this will be your t is from 0, 1. So the dot here, you got this is 37 square root of the 14t. What is my ds here? Hey, I just calculated here. It's here, right? So this is what is my ds. So what I times here, square root of the 14, right? So what here, dt is here. So 14, 14. So it will give me the 0, 1, 37 and over 1 to the what? So this is t dt. Wow, so you integrate here is super easy integration, right? So it's 37 over 2. So it's the same like we did by using the method number 1 here. Okay, so now let's take a look. The method number 3 here. How do I use components, right? Try to integrate that. Okay, so since we are in a different slide, so just let me write here again. So I know the f of x, y, z is equal to the px here is y plus z to the I plus 2x plus z to the what? To the j. Okay, so remember change your handout here and the plus x plus 3y to the case here. Okay. Okay. So now let's try to integrate this ones here. So that means I can use the components function. So this one going to equal to C. Okay. So I'm going to, so this is y plus z dx and plus what here, the 2x plus z dy, then plus x plus 3y dz here, okay? So now the x, y, z, just like we did before, right? So we know the x equal to the t, y equal to the 3t, z is equal to the 2t's here. Okay, so now let's take a look. How do we do the integration? I'm still changing to t's, right? So here, because it's line segment, t is 0, 1. Okay, so let's take a look. Y plus z. Y plus z. So it's a what here? It's a 5 what? 5t. Okay, 5t, I'm integrating to the dx, right? So this is the dx dt. What is here? This is 1. This is dy dt. This is 3. This is dz dt. This is 2, right? So the dx here, so what I need to put here? I need to put a what? It's 1, right? So this is the 1. So it's times 1 is nothing. So it's times dt. Okay, so now the second one is here, 2x plus z. 2x plus z is 4t, correct? So this is a 4t here. Now, but in here, I'm integrating for what? For dy here. So dy dt is what here? It's 3, right? So that means I need to times 3 dt. Okay, so the last term, x plus 3y. So x plus 3y, so it's 10t. And because what I'm in, so this is what? dz, right? So dz is what? It's 2 times 2. So now I change everything to where? I change everything to the t's here. And just let's do here. So this is a 5t, 4t. Okay, so no, not a 4t here. Okay, so this is a what? This is 12 t's here, right? This is how many t? 20t. So you can combine them. So it's a 5 plus 12 plus 20. What is here? This is 37t dt. So what is the, what is the integration? It's 37 over 2. All right. So it's exactly the same, all these 3 methods here. So the key things for this method here, you need to remember is it depends on the different, it's dx or dy, and then you need to choose the correct ones here, right? So you need to choose the correct one and to get it. Okay, so now let's take a look at our last problems here. Okay, the last problems here, we say I have a force field right now, all right? So I have a force field right now, and it's equal to x plus y to j here. I want to find the amount of the work done. Okay, so this is a physics application. I'm moving a particle along the parabola y equal to the x squared from 1, 1 to 2, 4. Okay, so what I did here, I show you what is it. I graphed the force field here, right? So this is xy. If you see, this is the force field, right? So that's what the blue one looks like. Then these red lines here, right? So it's from 1, 1 to 2, 4, from here to here. Those are this is the path I'm going to move this particle. So I'm going to see how much work have been done for this particle. Okay, so now let's take a look here, right? So we say, when we do this type of the problem, the hardest one is what? It's the parametric form. Correct? Okay. So, but this one is not too bad. Y equal to the x squared. So I can say the x equal to t. If x equal to t, y is pretty straightforward. So what's going to be T, y is here, t square. Because t, x equal to t, so it's equal to x. So what is my starting point and the ending point? I use the x's here, right? So x, the t is from the 1 to where? 1 to 2 is here. Okay, now after this is pretty easy right now. So I have a dx dt is equal to 1. dy dt is equal to the 2t. Okay, so now I'm going to, so let's try to do the work here. So this one here is C, this is F, right? XY dot dr. Okay. Okay, so now let's change that. So I'm changing to the t's, right? T is from 1 to 2. Okay, so I'm plugging, so x here. So the parametric form x equal to t. So what I have here, I have a t here, right? Okay, so I have a t here. And because this is x, so the dx is what? Dx is what? So I'm using these forms here. So the c, the pxy dx plus qxy dy here, right? Okay, so now you say here, qxy is here, right? So qxy is x plus y. So what is x plus y? So it's t plus t square. Be careful, see here. What is this one here? It's dy. So what I need to times here, I need to times 2t dt. Okay, that's right, because these ones, be very careful, you need to match, right? Okay, so now I have changed everything to the dt's here, so I can combine a little bit. So t plus t, so this is, so this will just be what? So t plus t, so this will be just 2t, no, here, okay, so here will be just like t, 2t, so this is 2t square plus what? 2t cube dt. Okay, so I assume everybody know how to do the integration for this ones here. So the integration here, so finally is 41 over 3. So I know the total work has been done by moving this article along this parabola. The work has been done is 41 over 3. Okay. And that's it. So this is the second video. So we talk about mainly is the line integral over the vector field. It's very similar like when we try to do the line integral over scalar field. So what is the things we need to do? Hey, make sure we transfer that, right? We find our parametric form of the path we are trying to integrate, then try to change everything back to a simple integration, right? A one variable simple integration. Okay, that's it. And hope this, hope this topic sounds interesting to you, and hope you enjoyed to learning about the line integrals here. All right, nice talk to you, and looking forward to talk to you in our next topic. All right, bye.